I'm getting there.
Probably not
I will
lighten us up into the school year.
Yeah, I'll see. Maybe Griffin knows about it. Maybe one day Griffin will watch this video.
Yes.
So one of the greatest Smash Melee players of all time just gets really drunk and plays party games on Twitch, and it's probably one of the best.
It's
things
great.
that happens.
Okay, so we're moving on to energy, rotational energy, and so a few days from now we'll just take a quiz that covers momentum and energy. Okay. So what we got to do. This question kind of is supposed to just walk you through the process of. So like always, we start with a point mass rotating. Okay. This is R. This is V. And so we want to talk about what's the energy of this system, but not in terms of M and V, because we know how to do that already. That's going to be 1/2 mv squared. Everyone remembers that, right?
Mm-hmm.
Okay, so that's kinetic energy. And so we're going to say, well, how can I maybe rewrite that so that down the road, if this isn't just a point mass, if it's maybe like a disk or a sphere or something rotating, then I can describe. You okay, Kate? You look tired. You pretty tired? Okay, yeah. Hopefully we're not too tired. This fine Monday. Okay. So if I want to get omega involved, what can I do? How can I relate V to omega?
R.
V equals omega R, right? So I can replace that V with omega R. Yay! And then we got, if I square that, that's omega squared times R squared, and then rearrange it, you have, and let's take the R squared and put it next to the M. Make sense?
Mm-hmm.
All right, now, do you see? Who dat? Now, isn't that lovely? Look at that. Do you see? So it's like, instead of being 1/2 mass times velocity squared, it's 1/2 times the rotational mass times the rotational velocity squared. Beautiful. Isn't that nice how it just works out? Again, that's one of the many reasons why we choose to define I that way. Makes it a useful quantity. So for example, if you double the velocity of a moving object, what do you do to the energy? Quadruple. Likewise, if you have a rotating object, if you double the rotational speed, you quadruple the kinetic energy as well. Okay. Now we're going to talk about real quick. If you exert an external torque on this system, you're going to increase its energy. So we've already talked a little bit about how this one, torque times time would give you a change in angular momentum. Yeah. So that's one way to think about it. There's another way you can think about it in terms of how the. So by the way, this was analogous to force times time gives you a change in linear momentum. So this is kind of these guys are buddies. The same thing is going to exist here, where does anyone remember the linear version of how a force can cause a change in energy? Keyword hint would be work. relates to work? No one remembers?
That's-
Force times distance gives you the change in energy. Remember, force times distance gives you, so this one is if you had a block, for example, if you exert a force over some distance, d, then at the end of that process, you will have changed the energy. That's called work. Work is equal to the change in energy. So what's the rotational version of this? Well, we're going to start with this formula. Change in energy is equal to force times distance. And the idea would be, well, if this is a force, so say we exert some force on the ball, here's the distance. So see what I'm getting at here? So the force is actually changing direction as you move it. But imagine you push this thing, let's call this some change in theta, some angular displacement. How far of a distance did you go if this is the radius? Remembers this one? Distance being this arc.
Isn't it? It's radius, or this cosine radius.
Man, I've really failed you guys. I'm sorry. Maybe one day.
I remember going over.
What's a radian?
Oh,
Remember, what's the whole point of inventing radians? The whole purpose.
We're gonna have Brad seconds.
That's pretty good.
The whole point of having radians, guys, is so that you can say that this arc length is equal to the radius times the angle. Okay? So this distance that you would travel along the arc is the radius multiplied by the angle that you turned by. Okay?
You know, Mr. Hall, if you don't want to be a teacher anymore, just go home, fire up Grand Theft Auto and be a cop. Or a prison guard, whichever one you want.
Yes.
I think we started.
I could get a job at Burger King within that environment.
Yeah.
After a few years of working at the virtual Burger King, then maybe I could get promoted to virtual assistant manager.
Assistant.
Assistant to the assistant
Yeah,
manager.
there you go.
You know, we'll see.
Goal for the
Anyway, so this distance, so I can say this distance is the radius times the angle. Okay, now, what do you think we're going to do next?
Oh, torque.
That's torque. Right there. Force times radius, that's a torque. That's what the torque is, right? So the change in energy, we're just shifting our perspective here, guys. So if you're dealing with things moving in a straight line, you can say that the force times the displacement is equal to the change in energy. If you're dealing with a rotational system, instead of force, you're talking about torque, okay? And instead of displacement, you're talking about angular displacement, okay? You feel okay about that?
Yeah.
Okay, great. All right, let's try to answer 2 and 3. While I erase the board here, you can get started. So number 2 is basically just asking, say you got a spinning object, can you relate the energy of that object to omega and L? So, and here's a place to start here. It doesn't specify what kind of object it is. It doesn't say it's a sphere or a cylinder or a point mass or anything. So just assume it's some object that spins and give it an I value of I. Just call it I. go from there. Just try your best. Man, this marker, some of these markers don't erase very easily. Need some candy, Kate? Need some breakfast candy? No? Ugh. Wonder if Griffin ever streams on Twitch. Griffin, you ever go live on Twitch? We'll see. We'll see if he ever comments. Sometimes he'll comment on a video that's like from a million years ago. He'll just be like, "Oh, epic gamer moment." Send us a link to your stream, bro. Okay. So. We got a spinning object. We don't know what it is. Say it was something really weird, like I don't know, it could be a pyramid or something, you know?
That's cool.
Could be anything, right? And I'm only mentioning a weird object just to emphasize the idea that we don't know the formula for the I value of this, but we can just say, well, it definitely has some kind of I value. Right? If you told me the mass and the dimensions of this thing, we could calculate it in theory, right? So then you'd say, well, what's the angular momentum of this thing? If it's spinning around with some speed omega. I won't ask you guys any more questions, okay? L equals I omega. All right, so, and then what's the energy? Because the question's asking, what's the energy in terms of L and omega? Is that possible to do that? Let's see. So the kinetic energy is 1/2 I omega squared, okay? And then so, let's see, take this guy, all right? And I could, what could I do here on my
You could
formula?
so substitute it and you have an extra omega.
Do what?
Oh, you can just substitute them in. If you split the W or the omegas, you got K equals 1/2 L.
Replace the I with?
MR squared.
L. Wait, why do you have to?
Because so guys, the question's saying, can you write the kinetic energy in terms of omega and L? Okay. So what I would do is I'd say, well, that guy's not an omega or an L, so I'd like him not to be there. So I'd like to replace him. And then you'd look at this top one and say, oh, that's nice. The I can be written as L over omega, right? So I replace the I with L over omega, and then I can simplify, and you get this nice relationship. 1/2.
Yeah, that's pretty.
Now, don't let this fool you. Because you might look at this and go, well, according to this, if I doubled omega, I would double K. Why is that wrong?
Because L also has an omega.
Very good. Yeah, L depends on omega. So if you doubled omega, sure, you'd also actually be doubling L. So you'd be doubling this and doubling this, so you'd be quadrupling K, which is the result we had a few minutes ago. Okay, so I want to go over 4 with you. Save 3, you can do on your own later. We're going to do 4, and then Maybe we'll do 4 and 8 and then be done for the day.
I wonder if you can DoorDash in that game.
Oh, Uber. Oh, that'd be cool, actually.
The dude apparently worked at I guess his job at the burger restaurant was a front for his criminal behavior. Because he committed a crime and then he went to work for like an alibi. So he worked at a burger restaurant, like a fast food burger restaurant. But he was off committing some crimes. Anyway. But I don't know if he has to like show up to that job periodically or he gets fired. Does he have to like?
Great
I don't know.
question.
Huh?
It's a great question.
Well, you don't know. I was genuinely curious if he has to like. Could you get fired? Yeah. Could you?
Not my cup of tea.
That's not. Well. Okay.
Yeah.
Here's Bob. He just threw a bowling ball. The bowling ball has a radius of, this is number 4, a radius of 20 centimeters and a mass of 6 kilograms. And a bowling ball, we're going to treat it like a solid sphere. It's pretty close to a solid sphere. Those holes throw it off a little bit, but close enough.
For government or?
He had them filled. He had them filled with some sort of epoxy that was the same density as the bowling ball material. So he's a very diligent astronaut. Okay, so this ball, notice the ball's not rolling, okay? The ball's not rolling. If the ball were rolling, you could write V equals omega R and maybe use that. But does that make sense how a freely traveling ball, it could be spinning super fast and traveling pretty slow, unlike a rolling ball where those two quantities are kind of tethered to one another. Okay. So, it's traveling with a linear speed of 8 meters per second. And it's also spinning with a, what is that? When it says 3 revolutions per second, that's F, frequency. 3 revolutions per second. So the question's asking, with all this given information, what's the total kinetic energy? So the first thing I want us to think about here is, let's say a ball is just spinning in space. Does that have energy?
Yes.
Yeah, the particles in that object are traveling. That means they have kinetic energy. But what if it's spinning and moving? Then that's more energy, right? You've got the energy due to the spinning, but you've also got the energy due to the traveling, okay? So what we're gonna say is the total kinetic energy is gonna be both components. So first, the kinetic energy from the spinning, which is 1/2 I omega squared. And then also the energy from it moving. You feel okay about that? Do you also see why it was necessary to make a point of showing that V and omega have nothing to do with each other? They're not related.
Yeah.
So let's carefully identify, do we have everything we need? We need omega, very good. So let's get, where can I get omega from?
2 pi F.
Yep, so omega is 2 pi times the frequency. So we know the frequency Might put a circle on everything I need to use. So 6 pi is gonna get used. How about,
Mass and radius.
we have the mass and the radius, which are gonna influence I. So I for a solid sphere is 2/5 mr squared. Did anyone's quackmulator get us a number here? This is 6, this is 0.2, so it's gonna be some kind of smaller size decimal.
0.048. Oh wait. I was corrected.
You could lump this formula into this equation and like kind of do it all at once. I'm feeling just calculate the I value. What, 0.096?
Yep.
Cool. And if I want to be really precise, I would add the units on. It's kilograms times meters squared. Kilograms times meters squared. What? All right, so now we got everything. So the I value for this solid sphere is 0.096. The omega value was 6 pi. Let's be careful to be squaring that whole thing, not just the pi, not just the 6. The mass was 6. The velocity was 8. And I can't find my quack. Oh, there it is. Mr. Quack, oh, later. I'm going to calculate these separately. So there's some food for thought. Why might someone want to have them separately for the moment? Huh?
Are you trying to keep it in terms of time?
Not really. I mean, I'm gonna have a pi squared in there, and he's not gonna have a pi. So I mean, I certainly could write this as like an exact answer, like we like to do in math a lot, but it's not really gonna. I mean, there might be some context where you wanted the exact answer, but no, it's not like a super duper important thing. I'm just wondering how much. What's the division of energy here? Like, is most of the energy due to the rotation, or is most of the energy due to the traveling? In this case, we're going to find so check that out. The vast majority of the energy is due to what? Yeah, the movement through space. This 8 meters per second is really having a big effect, right? So anyway, my final answer is 209. Okay. Joules, of course, is still the energy for the unit for energy. What,
You
Caleb?
should find the hypotenuse length of the triangle that's being formed on your board due to the sun. It is a nice triangle.
Well, if I could measure this and this with a ruler, I might as well just measure the hypotenuse directly.
Exactly.
Here you go, Caleb, just for you, bro. Because you're worth it. Here you go. I gotta make sure I don't block it. Okay, do you think I got it? 95 centimeters, almost a meter. Maybe in a few minutes, depending on where the sun is, we might get a full meter. That would be exciting.
Oh, that's cool. Living on the edge.
I know. You guys would lose your minds. All right, let's do one more thing before we're done. Okay.
Yeah.
Mr. Trenton.
You're not doing the problem.
Mr. Trent. Why so sleepy, Mr. Trent?
Yeah, that last problem really exhausted.
Really? And you get like an industrial lamp, like they use for nighttime construction projects, and just blast you with it. That'll keep you up, right, Trenton?
It would. Till midnight.
Midnight. That's late, bro.
I got more mac and cheese than I expected. My friend just leave it. It's like, eat it. Of course, it's like, it was like over the course of an hour. Because I got home, I ate some candy, and then I was all like, what the heck is mac and cheese? So then I watched the Falcon and the Winter Soldier while I ate mac and cheese.
How was that show? It's good.
It is good.
I'm almost through all the Marvel movies. I gotta say, I watched that Ragnarok movie, and I was like, dang, this is actually, I think it might be one of the best movies of the whole franchise. It's kind of I couldn't quite identify what I liked about it. Maybe it was the irreverence, I don't know. I thought it was kind of funny, but and it was like good, had some good sci-fi elements.
Which number is this one?
And the villain was cool in that movie. The villain actually made sense. It's like, finally. Fits into like the sort of mythos of the whole show, or the plot. Okay. Just a wee lad there. This little guy has a mass of little m. And this is a solid disk. Okay. This solid disk has a radius of r and a mass of big M. All right. What? So it's a classic energy question, okay? Which is how much, how fast will this thing be rotating if you just nudge this slightly? It's going to swing around to the lowest point. Now, of course, what would really happen is it would actually oscillate. Well, actually, if there was truly zero friction, it would probably, because you gave it a little bit of energy this way when you touched it, it would actually probably come up around and just keep spinning. But all it would take would be the tiniest amount of like air resistance or friction for it to go. That makes sense? Kind of like a little bit like a pendulum?
Yeah.
Okay. So how will we analyze this? With energy. So we have to determine, do you guys see, well, how to ask this?
Well, I was thinking like, because you have the, figure out the radius, well, you have the radius, right, for its height, and then you, so that's the distance it's gonna be falling with the effective gravity against it.
MGH.
Yes, yeah, very good. Good teamwork. This is going to involve MGH, gravitational potential energy. So the trick here is to go, well, this isn't the only way you can do it, but it's probably the easiest is to say, well, I'm going to call this my zero position. That's a height of 0, the bottom of it. Now, if you ignore the little globule there, the disk doesn't change gravitational potential energy as it rotates because of its symmetry. So really all you have to consider here is the gravitational potential energy of that guy. So what is his height?
2R.
2R, very good. Okay. So the initial energy of the system, so you might start off and say, well, initial total energy is equal to the final total energy. Okay. How much energy does the system have initially? It's not moving. Kinetic is 0, but
Potential is 2R times, 8.
well, yeah, MGH, right? Make sense? MGH. So that's the initial energy of the system is all stored as potential energy, MGH. And Then let's look at the final state when it reaches down here. How do I write? This is a little tricky. Maybe someone can figure this one out. How many things do I have to look at if I want to talk about the rotational energy of this?
Velocity.
We're solving for that. Just look at this. How many? There's two things, right? There's the disk. I guess what I meant by things is objects. Like there's the disk. I got to consider how about the rotational energy of the disk, right? And then how about the rotational energy of the actual point mass? That make sense?
Yeah.
So let's do the disk first. 1/2. What's the I value for the disk?
1/2.
It's
Yeah. So the I value for a disk, for a solid disk, is 1/2 mr squared, right? So in here, I'm going to put 1/2 big M. That makes sense? That right there is the I value for the disk. Plus, how about the point mass? It's just mr squared, but it's little m this time. Hopefully you're okay with distinguishing between the little m and the big M. Give the little m a little flourish there, a little tail, make him look fancy. Is this making sense? Okay. Oh, it's a bit of a mess here, right? So you've got over here, you've got little m g times 2r, and over here, can we factor out the omega squared? Let's factor it out from this and this. Now what's left over from this guy when I factor out the omega squared?
1/4.
This guy. You okay about that? And then, so your last step is to divide both sides by this whole mess and take the square root. And you might notice there's probably a way to write this a little bit prettier. Feel free to do so. But look at that. Ugh. But I kind of like the way it's written because it shows you where everything's coming from. This is the gravitational potential energy of the system. And this is two terms that relate to the disk and the point mass. You can see that omega depends on the square root of their ratio. So, all right, man. Another high energy Monday.